In section 2.2, we're going to continue our discussion with more on functions and their graphs. To start off, the next characteristics of function graphs we'd like to talk about are increasing, decreasing, and constant. Here are the definitions of increasing, decreasing, and constant. The most important thing to keep in mind about three different definitions here is when it's increasing, it basically means that it's going up as we move from left to right. For decreasing, it's going down as we move from left to right. And for constant, it's just a flat line from the left to right. Also, we say a function is increasing, decreasing, or constant on an open interval, which basically means the endpoints are excluded and we're using parentheses in interval notation when we talk about where this is happening. We also use numbers along the x-axis to write out the locations where a function is increasing, decreasing, or constant. So it'd probably be easier to look at some graphs and then determine increasing, decreasing, or constant intervals from there. So here's one graph, and we can see on the first part, it's going up as we move from left to right. That's where the graph is increasing. We're going to be looking at the x-axis to read off the numbers where it's increasing. It's increasing off to the left all the way up to -1. The interval would be called negative infinity to -1, where it's increasing. And then after -1, it's just a flat line, and so it's constant from there on out. As an interval, we say that's -1 to infinity. So it's increasing on the interval from negative infinity to -1 with parentheses, and it's constant on the interval from -1 to infinity. It's never decreasing anywhere. And so, again, keeping in mind that we're going to always use parentheses when writing the intervals for increasing, decreasing, or constant. Mainly that we do that because the number where it changes between the three different directions it could be traveling, increasing, decreasing, or constant, the locations where it changes are not locations that we ever include inside of any of our intervals. So we always use parentheses to indicate that those numbers are not part of increasing, decreasing, or constant intervals. Here's another graph to look at. Let's figure out where it's increasing, and then it's decreasing, and then it's increasing again, and then finally it's decreasing. We're going to read off the x-axis to determine the intervals for each. The first interval from negative infinity to 0 is where it's increasing. And then it starts to decrease. And the interval on the x-axis would be from 0 to 1.5. Since it stops right in between 1 and 2 there at 1.5 or 1.5. And then after that, it starts increasing again from 1.5 up to 3. And then from 3 onward to infinity, it's decreasing. So we say that it's increasing on the intervals from negative infinity to 0 in parentheses, and the interval with parentheses 1.5 to 3. It's never constant, it's never flat at any point, and it's decreasing on the intervals from 0, 1.5 in parentheses, and 3, infinity in parentheses. Connected to the idea of increasing, decreasing, and constant are the relative maximums and relative minimums, sometimes referred to as local maximums and local minimums. Basically, a relative minimum is where the graph goes down to a point and then immediately comes back up again. This in effect makes a valley in the graph where it goes down and then up. A relative maximum is where the graph goes up and then immediately comes right back down. This in effect makes a peak in the graph where it goes up to a point at the very top and then it comes back down. On this example, we're going to look at the graph and determine any relative maxima and minima. Maxima and minima are the plural form of maximum and minimum. So we could have more than one, so we say maxima or minima in case there's more than one. We notice that there are here 2 points in the graph where it goes up and then comes right back down. These are called the relative maxima, the peaks in the graph. And those occur at the points -2, 4 and 3, 2. We do have this one point down here where the graph goes right down to the point and then turns around and goes back up. We call that the relative minimum, or minimum in the graph, where it goes down into sort of like a valley point where it hits the low point, then turns around and comes right back up. That happens here at the point 0, 1. So that's our relative minimum. Here's another graph. We'll find the relative maxima and minimum if there are any. In this case, there are kind of some points up here up at the top where the graph goes up and down. However, it doesn't go right up and come right back down again. It sort of plateaus into a flat spot. So we don't actually have any relative maximum here, since it doesn't make a peak by going right up to a point and then immediately coming right back down. This is what happens when we don't actually get a relative maximum point. So it has, again, to do that exact shape where it goes right up to a point that comes right back down again. There's also no relative minimum either, because to have a relative minimum, it has to go down and come right back up. And we don't see that on any points down below. It might go down to that point, but it has to come right back up from there if it was going to be a relative minimum. So this graph actually has no relative maximum and no relative minimum. For this graph, I want to just take a look at it and see if you think you notice which points would be relative maximums or minimums, if any are actually here. In this case, there is one point where it goes right up to the point and comes right back down. So there'll be one relative maximum at the point 2, 5. On the other hand, there are 2 points where it kind of goes down to, but they are not relative minimums because it does not go down to the point and come right back up. So neither of those points make the shape required to call them relative minimum points. So we have one relative maximum and no relative minimum. The next topic about functions is even versus odd functions. An even function is a function where f of negative x is equal to f of x. That is, negating the input does not change the output. The function is the same with a negative x or with a positive x, either way. Even functions are what we call symmetric about the y-axis. And you can see that in this picture here, how that graph is what we call symmetric about the y-axis. The y-axis runs right down the middle, splitting the graph into 2 equal parts. An odd function is a function where f of negative x is equal to negative f of x. That is, negating the input does change the sign of the output from positive to negative. Odd functions are what we call symmetric about the origin. And next to it here, you can see what a picture would be when it's symmetric about the origin. The origin is the point in the middle where the x and y axis meet, and so that's kind of a symmetric point for this particular type of graph. To check a function whether or not it's even, odd, or neither even nor odd, what we're going to do is check what happens with f of negative x, or in other words, we're going to plug in negative x into the function. So for this first function, we're going to do f of negative x. So here we're going to replace the x with negative x, and so it would go negative x cubed minus 6 times negative x. Whenever I raise a negative thing to an odd power like the third power, it's going to stay negative. So this is going to be negative x to the third power. And negative 6 times negative x will be plus 6x. And so what we notice here is that this function now has a negative x cubed and a positive 6x. If we compare that to the original function, we notice that all the signs have changed. And since all the signs changed, that's one indicator of this being an odd function. So after plugging in negative x, noticing that everything changed here for the signs, we can make that conclusion of an odd function. Let's look at this function g of x equals x to the fourth minus 2x squared. We're going to plug in a negative x and do g of negative x. So we're going to have negative x to the fourth minus 2 times negative x squared. Notice how all the powers here are even. If we have even powers, then the negatives that are being raised to the power are going to go positive. Or in other words, the negative x to the fourth will change back into positive x to the fourth. The negative 2 is still going to stay negative 2, but the x squared, or I should say the negative x squared, will change back into positive x squared. So these negatives will go away due to the fact that they're being raised to the fourth power, which in the second power, and those are even numbers. So notice here how compared to the original function, nothing has changed. This is an indication of an even function. Now if we look at this function, h of x is equal to x squared plus 2x plus 1. We'll do the same thing that we've been doing in the last few examples. We're going to plug in a negative x and see what happens. Well, in this case, notice how negative x squared will change back into positive x squared. However, 2 times negative x will now be negative 2x, and at the end, we'll still have plus 1. Now, if we compare this function to what we started with, some things changed. Some of the signs changed, but not all of them. That, in this case, when we have just term by term type of functions, is an indication that the function is neither even nor odd. And this is just again sort of a rule of thumb that we can use to see if we have an even or an odd function. For most simple types of functions, like this one, we have just exponents and multiply, add, subtract, things like that. This would be the easy way of telling whether or not it's even, odd, or neither. Looking at if the signs changed or did not change, or if some but not all changed. And now in this case, this would be an indication of neither even nor odd. Now if we look at this function, this one's a little bit different since it has a square root. So some of the rule of thumbs that we were using in the last few don't really apply here necessarily. We do check though by plugging in negative x. So if we plug in a negative x here to the function, here's how it's going to go. We'll have negative x times the square root of 1 minus negative x squared. Since that's x squared, we're going to have negative x and the square root of 1 minus, and that will change back into a regular x squared. Now in this case, the way to tell if it's even, odd, or neither is to look at everything here. Everything here is the same identical function as f of x. The only thing that's different is there's a negative out in front. So another way of looking at this is equal to negative f of x. So what we say here is we can tell that f of negative x is the same thing as negative f of x, a negative out in front of the original function. That means, by what the definition of even or odd referred to earlier, that means that f of x is odd. For this next example, we're going to be looking at the graph and going back to the idea of symmetry within the graph to determine if we're dealing with even, odd, or neither functions. In this particular graph, it does have what we would call y-axis symmetry, since it's evenly split on either side of the y-axis. So since it's symmetric about the y-axis, this graph is generated by an even function. This next graph, on the other hand, looks like it's sort of symmetric, but in this case it's symmetric on either side of the origin. It's sort of a reflection on either side of the origin here. So since we have symmetry around the origin, this graph would be generated by an odd function. So to tell if it's symmetric about the origin, look at points that are connected by a line that goes through the origin like I did here. And if the origin sort of is in the middle of that line between 2 points on either side, then that means it's symmetric about the origin. The origin's kind of in the middle between the different points on either side of that line. Now on this next graph, the graph is a little bit different. We don't really have any symmetry when it comes to the y-axis or the origin. So when we don't see that either one of those symmetries, it would be neither an even nor an odd function that goes along with this graph.